We present our findings on the use of synthetic data in supervised learning, namely domain randomization for the task of image classification as published in the Journal of Big Data. We make use of the power of the Unity game engine for our image generation over other graphic rendering tools for its speed at the cost of photorealism. A typical photorealistic image can take hours to render, making the process impractical for a large dataset without the use of rendering farms, which are often complicated and costly endeavors. We begin with the two-category classification problem between cats and dogs. In order to generate a dataset as diverse as possible, we randomize a bunch of different parameters. Namely, we sample a bunch of different breeds of our subject in a variety of different poses. Our camera is randomly placed in the scene with the subject visible. Occluders are placed in random locations and directions in the scene. Finally, skyboxes, lighting, and textures are varied across each capture. In order to keep our study focused specifically on the effects of the synthetic data on the overall accuracy, we keep the tuning of the network architecture to a minimum in our tests. We utilize a VGG16 base as a feature detector and stack a 128 neuron dense layer before the final classification. We test whether keeping the VGG16 base weights fixed and the addition of dropout into the network have any effects on the model performance, but further optimization into optimal network architecture for the synthetic data was not conducted. We train the models using real and synthetic images and evaluate their performance strictly on real-world images from the Kaggle cats and dogs dataset. We show that an accuracy of 85.78% can be achieved using only domain randomized data. Dropout appears to have negligible effects, while unfreezing the weights of the VGG16 base severely degraded the overall accuracy in our experiments. We aim to gauge the importance of each parameter in the domain randomization process and proceed to generate new datasets with each parameter omitted. Our results, when evaluated on real-world data, imply that the variation in subject breeds is by far the most important parameter, as might be expected. Other parameters appear to influence accuracy, but only marginally. Interestingly, the removal of the occluders and variation of subject poses actually increased accuracy, suggesting important features used for the classification are hidden in the initial synthetic dataset. With this in mind, we are able to increase the classifier's accuracy up to 88.26% entirely using synthetic data. It is also of interest to us how the model will perform when tested on other domains. We gather a dataset from publicly available images of cats and dogs from cartoons, as can be seen in the bottom row, and proceed to evaluate our models across each of the domains. We find that the model trained on synthetic data does not transfer well to the tuned domain, achieving an accuracy close to randomly guessing, while the model trained on real data managed to get up to 76.5%, suggesting substantial gaps between domains. However, the real trained model also struggles to correctly classify synthetic data at 65.5%, suggesting important features are still missing even in the real data when it comes to generalizing to other domains. Overall, the model trained on synthetic data outperformed the one trained on real data on average out of domain, as can be seen in the final two bars on the right. We also explore the effects of a larger number of categories in the classification and the region of interest the model prioritizes when making its decision in greater detail in our paper. We invite viewers to see the full publication available at the link provided.